Hello everyone, welcome back to Power System, class number 4. Today we're going to talk about three-phase AC systems. Most generation, transmission, and most of the distribution are in three-phase systems. Three-phase system means the voltage and current, they're all balanced. That means they all have the same magnitudes, but they're apart from each other by 120 degrees. So that is called three-phase balance system. One is magnitude is same, but they're apart from each other by 120 degree. So here you can see that positive sequence and negative sequence. In positive sequence, if this is the reference over here, so I can say that E, A, N, let's say 120 volts, 0 degree angle, then E, B, N over here to be same magnitude, but your degree over here is 120 and you're going clockwise, there should be negative 120 degree. And if you come up to here, you get another 120 over here, right? And 120 over here. So ECN would be again same voltage, negative 240, or you can say it 120, positive 120, same thing. So this is called positive sequence. And in this positive sequence, we go A, if we go clockwise, A, B, and C. And that is mostly we're going to use in this course, which is positive sequence. And your negative sequence, when you go A, C, B in clockwise, then you can see that you're, again, if this is your, let's say 120, 0 degrees reference, and this one would be 120, negative 120 degree, and this one would be here is 120, negative 240, or 120 magnitude, positive 120 degree. So we're going to use this one over here for our course, which is positive sequence A, B, C in clockwise direction. So in three-phase systems, if you multiply instantaneous power for three-phase, you will see that your real power and reactive power does not have any time-varying component. So your real power over here for three-phase is a average value. There's no time-varying component in there. Whereas single-phase, you have this one here and also have time-varying component, and this one is all time-varying component. Over here, this one has the what do you call it? Same over here, but in 3 times with respect to the phase. But the big thing in three-phase power is that you don't have for real power does not have time-varying component. All right, so real power in three-phase power doesn't have any time-varying component. What is that? Your real power in three-phase is a constant value. All right, so when you're doing work or operating a motor, your motor operates at constant speed. On the other side, if you look at this, the three-phase over here, if you look at the single phase, it has this here. This is the single phase power. What does it mean? Your motor has a pulsating power, so your motor goes like this. So it's not have a constant output on the shaft. All right, in three-phase you have 2 different connections. Y connection right here. This is the Y connection, and delta connection right here. So Y delta connection is kind of you need it for some advantage. We're going to talk about that. And also sometimes some load can come as a delta connection or Y connection, and you need to understand what the connection means. For Y connection, you have a neutral point over here. For delta connection, no neutral connection. Right? So let's understand some very basic things over here. You have Y connected generator and Y connected load. So both are Y connected. So their common neutral is connected to each other, but in practical transmission line, this neutral is virtual. What that means, ground is used as neutral. So neutral is universal ground. So if your generator is connected to ground and your load is connected to ground, that means it's virtually connected. All right. Okay. Over here, this is called excitation voltage. The voltage actually generated by the generator is called excitation voltage. All right. So this excitation voltage over here, EAN, and this is the reference over here. As again, we're using positive sequence, so this is the negative 120, this is negative 240, right? So now if you come to this point over here, you have to subtract whatever loss into this one here if you're carrying the current IA. So now if you come over here, right here, if you're trying to come over here, then you have to also subtract the loss over here. So that's VAN, which is basically this one here at this point, minus whatever loss over here. So if I go further from here, it would be, let's say, EAN negative ZZ, which is generator, IA negative ZL IA, right? Then you can say that you can also write the same equation for other two, like these two over here, only changing the symbol over there. So if I do that, BN over here, it would be EBN negative ZB, and IB over here, negative same load, and IB over here. All right, and obviously you can now write VCN. I'm not gonna go there. So for a Y connected load, so how does it work? Relation between the voltages over here. So for a Y connected load, over VAN over here is also same as your phase voltage, right? So why is saying that phase voltage over here? Let me draw a little symbol over here. So this is the load over here. Right? So let's say this is your phase voltage for this phase, and it should be same for all the phases, right? Right? So if you come over here, let's say this is your VAN, this is your VN, this is your VCN, right? So this voltage VAN with respect to the neutral over here, same as your BP, same magnitude, right? So magnitude doesn't change over here, and this is the reference. You can use that as reference. Then this one over here would be same voltage, and angle is 120 degree, negative 120 degree apart from there, and this also and negative 240 here, right? So now, if you're trying to find the difference between A and B phase, we have BAB, BAN minus BBN. If you're trying to difference between them, so we're gonna subtract this one from this one here. So that's so your common voltage comes out. Then you have 0 degree and negative 120 degree. If you do the math in your calculator, you will see that this is what it is. So what it means that your line to, it's called line to line voltage over here. So line to line voltage over here is basically square root of 3 times than phase voltage, and there's angle difference of 30. So this angle is right here, you can see that, and this is the magnitude. Magnitude is square root of 3 times higher than your phase voltage. From that one, you can easily write this one here. Before I write it, let me draw it. So all the line to line voltage would be shifted by 30 degree from their respective line to neutral voltage. So this is also a 30 degree over here, right? This is also a 30 degree over here. So if I look from the reference, if I look from the reference over here, so this one is 30 degree, right? And this one BC over here, it would be same magnitude, right? Then angle would be 90 degree, negative 90 degree from the reference. Negative, this is the negative 90 degree from the reference. And we see over here, so from the reference, if I go, again, if I'm going clockwise, so negative angle 90, then you have 120 plus 30. So you can, same magnitude, you have same magnitude over here, your angle would be negative 270 for that one, right? So that's how you go from line to line to neutral, or line to neutral to line to line. So line to line voltage and line to neutral voltage have 30 degree angle difference there, and line to line voltage has a, so this is 210, not 270, it's 210, has 30 degree phase shift from the line to neutral voltage. So now, for the current, obviously you have your voltage over phase impedance. So line to neutral voltage from here to here, from here to here, and impedance, you get the current, and this is the angle for the current IA, and IB obviously 120 degree, negative 120 degree apart from there, and IC negative 240 degree apart from there. So that's your current. This theta is the phase shift between voltage and current. For delta connected load, you can see that over here. Let me go back mention one thing over here. For this, let's see, no. Let's see over here. So over here, your current IAB is current from this point to this point here. This is A, this is B, this is C point. So IAB is IP, which is a phase current right here, and 0 degree angle. So now you go IBC, it will be what? Phase current, same current, and 120 degree apart, negative 120 degree, and CA is the same over here. So your IA, which is line current, line current over here would be, if you look at line current over here coming in, and this also coming in, so that would be this one minus that one. So let me go that over here. Let's see. So IA is this current minus this current over here. So if there's a KCL, if I have like KCL over here, so IA, let's do it, is coming in, negative IAB, and also ICA coming in, right? Should be equal to 0, it's KCL, right? Then your IA would be IAB minus ICA. That's right here, right? So if you do the same math, look at here. Almost the same. So your for the delta connection, your line current is square root of 3 times higher than your phase current, and also 30 degree phase difference bit right there. So this right here. So IAB and IA, there's a 30 degree phase difference over here, and this one has square root of 3 times magnitude than your phase current. And you can now do IB and IC. So if you do IB over here, your IB with reference to the A over here is, so it would be 120 plus 30, so it would be negative 150. So it would be your current over here, it would be square root of 3 IP. There is no difference in magnitude. Your angle would be negative 150 degree for IB. For IC, it would be square root of 3, no difference in magnitude. Your angle would be negative 270 degree right here. All right, or you can also say that this would be square root of 3 IP 90 degrees, same thing. All right, so that's how your current related in the delta connection. So if I summarize that, for Y connection, your line to line voltage has a higher magnitude by square root of 3 times than phase, and angle difference 30, and line current is phase current, because line current coming here is also going to the phase, so same current, right? For delta, So line to line voltage from here to here voltage is same as your phase voltage here. So line to line voltage, the phase voltage, same thing, but your line current is square root 3 times the phase current, and angle is negative 30 degrees shifted from the phase current. All right, so that's all for three-phase AC systems. We're gonna go to three-phase circuit analysis next. We're gonna do it at part 2.